Hello, I am Professor Ali El-Bahrawy from the Faculty of Engineering Ain Shams University. Today's lecture is an introduction to network hydraulics. There are three types of hydraulic networks that we are going to study. One is for pipe irrigation, the second for water distribution, and the third for drainage collection. Each of these three types have different details that we are going to discuss together. This irrigation network of pipes under pressure takes water from the source at certain elevation and pump water to a sprinkler irrigation system at the terminal nodes numbered 5, 6, 7, 9, and 10. The other type of network is a water supply network with two reservoirs, two pumps, a pressure reducing valve, and some other valves. It's a completely different network with different purpose, but it also supplies water from the reservoirs through the pumps into the demand nodes shown in the network numbered 1, 2, 3, and 5. The third network is a collection network used for sanitary or wastewater. A triangular node is inflow and a circular node is outflow. In this network, as you can see, water is collected from the triangular inflow nodes and ends up in the last circular outflow node number 10. There are two types of flow, pressurized and gravity. For a pressurized network, as you can see, the water is filling the cross-section. Here, water flows due to difference in pressure. In the example, you can see a pipe, a pump, a valve, and a sudden enlargement, then a gradual contraction ending with a pipe with a smaller diameter. The lines you are seeing are the total energy solid line and the hydraulic gradient dotted line, showing the loss of energy throughout the system from the start to the other reservoir at the right hand side. The design variables here are the diameter, flow, and pressure. For gravity pipes, you can see that water does not flow due to difference in pressure, but due to difference in elevation, because water flows by gravity and water doesn't fill the cross section. There are two examples of partially filled pipes at the bottom of the slide. The design variables here differ from the previous pressurized network and include, in addition to pipe diameters, excavation depths for calculating pipe slope. Another issue is network topography, which is the relation between nodes and pipes. Here we have two main categories, tree network and loop network. This is an example of a tree network where you don't have closed loops and water is coming from node 1 to supply nodes 3, 4, 5, 6, and 7. As you can see, the loop network here has 4 closed basic loops where water enters node 1 and is distributed to nodes 2, 3, 4, 5, 6 up to 9. Here we put node numbers between square brackets and pipe numbers between parentheses. There are three types of problems for the loop network. Analysis problem, external flows and pipe characteristics are given and it is required to calculate pipe flows. A design problem, location of nodes and external flows are given and it is required to locate and calculate size of pipes, pumps, reservoirs, and other network components. There are two design problems, one for layout and the other for network components. The last type of problem is optimal design. A suggested design is given and it's required to find the minimum cost design. Such optimization problem can apply to the layout design and to the optimal combination of pipes, pumps, and other components. Most of the hydraulics of networks are governed by two main equations. One is a continuity equation, and the second is the head loss in closed loops. We define continuity equation applied at each node, where the sum of inflow to the node is equal to the sum of outflow. In terms of energy equations applied to closed loops, the sum of the head loss in pipes with direction of flow is equal to 0. To solve the three types of problems mentioned previously, we can use different variables. We can use flow or Q, head or H, corrective flow delta Q, or corrective head delta H. To show you how the four variables are expressed in terms of equation, you can see the first equation, head loss is a constant multiplied by Q raised to a certain power n. The second equation, Q from node 1 to node 2, is calculated in terms of H, and the third equation calculates corrective flow using the continuity equation. The fourth equation calculates corrective head using the energy equation. We are going to use a sample network of 4 pipes, 1 loop, 1 source, which is a triangle, and 3 sinks, which are the circles. Numbers are given for pipes and nodes between parentheses. Now I will give examples of equations using the 4 types of variables for the sample network I covered before. You can solve the analysis problem for the network using Q as variable by using 3 continuity equations, linear, and 1 energy equation, which is nonlinear. Because the number of linear equations is in most cases greater than the number of nonlinear equations, a simple solution to this system of equations to linearize the nonlinear equation as shown in the last line, then updates the approximate loss constant with each iteration until we arrive at the solution. Here we can see how to solve the same problem by using H as variables, and the equations you see here are 3 independent continuity equations at nodes 1, 2, and 3. Because the network is balanced, that's to say external flows is equal to internal flows, we don't need a force continuity equation. We have 3 independent equations for the variables H2, H3, and H4. Here we can use the delta Q system where we write only 1 loop equation in terms of delta Q because there is only 1 loop. The solution is called Hardy-Cross single adjustment. Here we have 3 continuity equations in terms of 3 different variables, delta H2, delta H3, and delta H4. We can use Hardy-Cross again to solve for delta H single adjustment and for each node. But it's better to solve the system of 3 equations which are nonlinear. How to solve the previously given equations? We have 2 approaches relying on the type. If the equations can be linearized, we can use a set of linear equations, but most of the equations are nonlinear, and we use what we call Newton-Raphson method. We are going to show you the algebraic details of how to solve these 2 systems of equations. A system of linear equations is shown where the first equation is a11x1 plus a12x2 up to a1nxn equals b1. We have coefficients for the variables x1 to xn, and we have right hand sides b1 up to bm. We solve this system using algebra by writing the above equations first in vector form as shown. We can also use the matrix form where A is a matrix of the coefficients, X is an array of variables, and B is an array of right-hand sides. By doing that, we can calculate X by inverting the coefficient matrix A and calculate X as A minus 1 multiplied by B. Therefore, in order to solve the set of equations, we need to invert the matrix of coefficients. With respect to nonlinear equations, we use the Newton-Raphson method. The equations are written to have the right-hand sides equal 0 to form a set of equations like the one you see. And they can be rewritten in compact form as f of x equals 0. Here, to solve the problem, we use the Newton-Raphson, where we calculate the f of x naught plus delta x naught equals 0. Using approximation by the Taylor series expansion, we can calculate f of x naught delta x naught equals f of x naught plus j naught delta x naught, where j is the Jacobian matrix. Jacobian matrix is a square matrix that differentiates the first equation with respect to the variable. Therefore, we have in the first row partial f1 partial x1 and partial f1 partial x2, and the last element is partial fn xn. Because we seek to make f of x naught delta x naught equal to 0, we can compute delta x naught as minus j naught minus 1 multiplied by f of x naught. We can update vector x as x1 equals x naught plus delta x naught. In general, we can update vector x as x nu plus 1 is equal to x nu minus j nu minus 1 f of x nu, where nu is the iteration number. Spreadsheets are powerful tools to perform such calculations to solve both the linear and nonlinear system of equations, because we can simply use functions to multiply and invert matrices like M mult and M inverse. Another important issue is how to name pipes. For tree networks, the naming is very easy because the direction of flow is known before we do the analysis problem. We use downstream nodes to name distribution pipes and upstream nodes to name collection pipes. We don't need to have different names for the nodes and pipes as for looped networks, where the only way to specify a pipe with its flow direction is to use origin-destination pairs. This example shows naming of pipes in a tree distribution and collection networks. For distribution, source is node 1 and sinks are the rest of the nodes. For collection, sink is node 6 and sources are the rest of the nodes. The table shows the naming of pipes compared to origin-destination pairs. Another problem is the location of pipes on plan, which is called the layout problem. This problem has a separate design and optimization models different from the analysis, design, and optimal design for a network with known layout. The network layout problem for a tree is simpler than that for a loop network. The main concern for the loop network is the level of service reliability. Usually, if you have one source and different sinks, we can transfer water to the sinks using a tree network. But this will have little reliability, because if one of those pipes is broken, some links will not receive water. This is the reason we should add redundant pipes. Redundant pipes are added to the tree network to improve the reliability in case of pipe break, and when we increase the number of these redundant pipes, the reliability level will be enhanced and increased. This is an example of a water supply network with one source. The tree network that supply water to nodes 2, 3, 4, 5, 6, and 7 are shown as continuous lines, and the redundant links are shown as dotted lines. When we increase the dotted lines, we increase the reliability. We can also count the basic closed loops 1, 2, 3, 4, and 5, which is the same number of the redundant links as we will see in the topology section. Description of flow is another issue, because tree networks, direction of flow is known before analysis or optimization. For loop networks, the direction of flow may change according to changes in pipe diameters and external flows. We can't decide on the direction flow in pipes before solving the analysis problem. This is a sample exercise for collection network where we have 11 sources and 1 sink. It's required to find flow direction pipe names. For the loop network, we know the direction of flow in the tree network where we want to transfer water from the source 1 up to the nodes 2, 3, 4, 5, and 6. But when we add the redundant links shown by the dotted lines, the direction of flow may change as we mentioned before. The topology of the network allows us to make simple calculations for the tree layout where the number of pipes will always be the number of nodes minus 1. For a loop network, the number of independent loops is the same number as the redundant pipes, and the number of redundant pipes will be the number of pipes minus the number of tree pipes. We can check the previous network to make sure that these relations are valid. This is a simple exercise to apply the relations given in the previous example to count the number of nodes, number of pipes, and number of independent closed loops and apply the equations of topology relating these numbers. Calculations of pipe flows is simple for tree network because we go backwards until we reach the source. In case of loop networks, we need to solve a set of simultaneous equations as we have shown previously. Another example for a pipe irrigation network where we are asked to name the pipes and calculate pipe flows. If every terminal node withdraws 4 cubic feet per second, the terminal nodes are number 5, 6, 7, 9, and 10. Here, the spreadsheet can help us calculate the tree flow even though it's simple, but sometimes the network has too many pipes and calculating backwards is a bit intricate. We can use the SUMF function with the solver add in to develop a simple linear programming model to solve the problem. This is a spreadsheet of the model showing SUMIF function and the solver window where we input ranges for target cell, variables, and constraints. As we have now covered all the objectives of this lecture, I would like you to make a matrix to compare between the different aspects of network hydraulics in terms of layout variables for calculation, solution techniques, and other aspects. Hope you enjoyed my lecture, and I hope the lecture has an added value to those who are interested in hydraulics of networks.